methods of search for the groundwater. If you go back and look into the ancient times, our society was dependent on the groundwater resource apart from the surface water resources, and they did have certain techniques which we call them as a dowsing techniques, and therefore, persons they used to search for the groundwater by taking a Y-shaped twig of the tree, hold it in hand, which you can see in the picture, and just go around, and when that particular twig changes its direction from above to below, then the person identifies the spot. Of course, there are a lot of doubts and there is a debate also about this particular techniques. Slightly there is a changed version of this, that there are copper rods which one can hold in the hands, and then one can try to use those copper rods, and when they cross like that lady in the picture, this particular crossing indicates that there is a likelihood of occurrence of a groundwater. Although there is a lot of discussion and debate and also doubts about this particular technique, this technique has survived for centuries from ancient societies even in the modern society, and therefore, we have across many developed countries and also in India there are many dowser societies. Without going into details of this particular traditional technique, we are now going to see that this is at the back of our mind, and therefore, we have to see now beyond traditional techniques, do we have the techniques which are modern scientific techniques, and can they be applied in search of a groundwater. And let us now try and look at these methods, and therefore, we have looked at this topic which is the geophysical methods of groundwater exploration. Now, let us go and see the applications of the method which is a geophysical method. Geophysics plays an important role for characterizing the groundwater in the hard rocks, and therefore, it has large number of applications. If we can see, this is something which is going to help us in terms of mapping the depth and thickness of the aquifers. So, within the subsurface, how much is the depth at which groundwater resource is located, and secondly, what really is the thickness of this particular aquifer which is present below the surface. Plus, it gives you an idea about mapping of certain layers of aquifers, and therefore, these are the kinds of layers within the rock which are devoid of water, and therefore, we need not really look at them, but we can actually map these aquifers also or confining layers below which there is a possibility of getting water. Plus, we have the groundwater which is essentially present in the rocks or soils only because of certain features, and therefore, locating these features is very important. Such features are fractures and fault zones, and therefore, these are conduits for the occurrence of the groundwater, and therefore, these conduits need to be located, which we can locate with the help of geophysical technique. And then mapping of the contamination of the groundwater is also possible. These days, lot of toxic waste is injected into the subsurface, and this toxic waste is really going to cause lot of pollution of subsurface groundwaters, and therefore, this particular subsurface water which gets contaminated, we need to identify what really is the plume of contamination, and this contamination plume can be very easily mapped with the geophysical techniques. In certain areas like coastal areas where we have the problem of salt water, and therefore, many groundwater resources you see that there is an intrusion of the salt water into it, and therefore, we need to really look at the interface between the fresh water and the salt water. Location of this interface is very critical in terms of searching for the groundwater or in terms of locating a well which will tap only the freshwater resource, and that is something which we need to really identify, which is possible with the help of the geophysical technique. And therefore, these are wide applications which the geophysics has provided, and therefore, we need to look at these methods. I just mentioned that we can map the fractures and faults within the subsurface by using the geophysical technique. And therefore, we need to also see what really is the importance of these fractures, because fractures often serve as a major conduit for the movement of water and also for the dissolved chemicals in the water. Fractures also lead to development of high permeability and also the porosity within the rock. Without porosity and permeability, the groundwater cannot be stored in the rocks, and therefore, porosity and permeability are very important properties from the point of view of occurrence of groundwater, and therefore, we can actually understand the very importance of these properties. And also the porosity, permeability, fractures and faults, they provide rapid transport for the movement of the water and also the dissolved salts with it or contaminants in it, and therefore, that is very important aspect of the fractures present in the rocks. In the area around whole of the region like western Maharashtra or whole of Maharashtra and all southern India states, whole of Indian peninsula, from the point of view of hydrogeology, from the point of view of groundwater occurrence, the peninsular India is characterized by hard rock aquifers. We do not have soft rocks, we do not have sedimentary rock formations largely present in this particular area, and therefore, all the aquifers or groundwater that occurs within the subsurface is only in the hard rocks, and therefore, we need to look at what really are the characteristics of these hard rock aquifers. And therefore, these characteristics are narrated in this particular picture here. Basically, the storativity and transmissivity properties, they show often large amount of variation in these kinds of hard rock aquifers over a small distance, because fractures or pores or fissures or cracks or joints which are present in the hard rocks, they are not uniformly present across the distance on a spatial scale, nor vertically also, and therefore, this needs to be understood from the point of view of occurrence, because without sufficient storage and transmission property of the aquifer, we cannot have exploitation of groundwater in economical quantities. Secondly, the topographical basin or sub-basin generally coincides with the groundwater basin. From geomorphological point of view, if we really look at the groundwater resources within the subsurface, then you need to follow the topographic trend in terms of searching from the groundwater resource, because as on the surface water flows, similarly is the case within the subsurface from higher level to lower level groundwater is going to move, and that is typically going to decide the characteristics of the hard rock aquifers. Plus, saturated portion of the weathered mantle or alluvium or laterite overlying the hard rock or fractures often makes a significant contribution to yield obtained from the dug wells or bore wells. And therefore, what really is the saturated thickness of this particular weathered zone needs to be identified, and therefore, that is something which one has to look at from the hard rock characteristic point of view. All these characteristics can be very easily determined by using the geophysical techniques, and therefore, we now see the basics of geophysical technique. There are large number of geophysical techniques which are in use. They are seismic, they are gravity, they are magnetic and electrical. Out of all these four techniques which are actually present for us to be used for hydrogeological exploration, the electrical resistivity technique has gained popularity simply because of the ease with which you can use this particular technique, the economical aspect and every other aspect, and therefore, electrical resistivity technique we are going to focus more on this particular topic. Basically, the typical definition of resistivity is given in my presentation here. If you consider L is the length of the conductor and A is the cross sectional area, then the resistivity you can find out R is equal to rho L by A. So, L is the length of this particular conductor, A is the area, and based on the ratio of L by A, you can find out the resistivity of a given medium, and therefore, this resistivity is measured with the help of this particular technique. There are certain kinds of properties of the rocks which we determine by using electrical resistivity method, and therefore, what really are these electrical properties of the rocks, that also we need to look at. One of the properties is resistance, and therefore, what is resistance? Resistance is V by A. V is the potential and A is the area, and therefore, this particular resistance is measured in ohm, and therefore, ohm is a unit used for measurement of a resistance in a conductor that produces potential difference of 1 volt. V is the voltage, and when a current of ampere 1 ampere is flowing through it, and therefore, this is how you can measure the resistance. Typically, Ohm's law is going to be used in this particular technique, and therefore, I is equal to V by R, and therefore, I is the electric current that you are passing, V is the voltage that you are measuring, and R is the resistance, or other words, R is equal to V by I, potential difference divided by the current. That is how this particular basic law, Ohm's law, is used in the electrical resistivity technique. And therefore, now let us try and understand the basic difference between what is resistance and what is resistivity. And therefore, resistance is nothing but it is a relevant only for a particular measurement circuit, and resistivity is an intrinsic property of a physical material, and therefore, these are typically two important properties that we need to understand the difference between them. Whereas, in the case of the rocks, we use often the term apparent resistivity, which is a resistivity estimate based on assuming half phase geometry, and this is typically what we use in terms of measurement of the geophysical properties of the rocks within the subsurface. Resistance is measured in terms of ohm meters, or other words, conductivity is measured in terms of mho per meter. There are certain properties of the rocks which influence the passage of electrical conductivity in the rocks. For example, as I said, porosity is one of the important property, volume of pore space, pore saturation, amount of water present in the pores, that also is going to affect the electrical properties. Fluid saturation, it could be hydrocarbon, water salinity or clay content, metallic sulfide mineral content, fluid temperatures and rock matrix intrinsic resistivity. These are typically the factors which influence the electrical resistivity or conductivity of a rock. There are no fixed limits for the electrical resistivities of different rocks. If you really look at the igneous rocks or metamorphic rocks, we have very wide range of electrical resistivity values, ranging from 10 to the power 2 to 10 to the power 8 ohm meters. And therefore, one cannot say that this particular rock will have this much amount of electrical resistivity, because the electrical resistivity is affected by large number of properties, including porosity, permeability and pore saturation and many other aspects, and therefore, this value cannot be fixed for any particular rock. Plus, if you really look at the other types of the rocks, which are soft rocks or sedimentary unconsolidated rocks, they will have range from 1 to 10 to the power 4 ohm meters. And therefore, from these two ranges, one can say that there are no fixed values for resistivity of different types of the rocks. As far as the groundwater exploration is concerned, we have the technique which we know that it is a geophysical techniques, electrical resistivity technique, and therefore, it is applied at the surface, and therefore, surface geophysical method is something which is also a term that is used by us. In this particular technique, the scientific measurement of physical properties and parameters of the earth subsurface formations or contain fluids are measured by the instrument located on the surface. Just as shown in the figure, you are actually going to locate the instrument on the surface and going to measure the subsurface properties of a subsurface medium, and therefore, this is something which is actually done in the surface geophysical method. Success of this particular method depends on how best the geophysical parameters are interpreted in terms of hydrogeology. This is one of the most important aspects of this particular technique, that you may apply the scientific method, but application of scientific method requires thorough understanding of the subsurface from the geological and hydrogeological point of view. Without understanding hydrogeology and geology of a given area, your success rate of locating the proper spot for groundwater exploration may not be successful, and therefore, success depends on how best you can interpret the subsurface conditions. An accurate interpretation therefore requires supplementary data from subsurface navigation to substantiate surface finding. I would say that what is the data that you can have? The data that you can have to characterize this particular technique in a given area is to look at the known sections. Known sections, they could be road cut sections, they could be wells within the area. Characterize the subsurface by using surface geophysical technique, which is electrical resistivity, and then see values of the resistivity which are actually obtained for the known subsurface section, and that is the analogy that you can use, and then you can go ahead with the unknown areas. Basically, this is what helps us in getting proper results, and interpretation they will match well. In the electrical resistivity method, current is introduced into the ground through a pair of current electrodes. So, we have two current electrodes, this is typically 4 probe method, and therefore, we have two current electrodes C1 and C2, through which current is introduced into the subsurface. And then the resulting potential is measured between another pair of potential electrodes, and therefore, we have P1 and P2 as two potential electrodes. By using these potential electrodes, one can measure the potential at potential difference produced at these two electrodes, and then apparent resistivity is calculated by taking equation into consideration. For example, rho apparent is equal to 2 pi a delta V by I, because we use 2 pi a because of the half pace geometry concept, and then delta V or V is the potential difference, I is the amount of current that we pass through the current electrodes or pair of current electrodes, and therefore, it is possible for us to get apparent resistivity by using the electrical resistivity technique. This is typically what we have the picture in which one can get an idea about how the current lines are produced between the C1 and C2, which is a current electrode. This is a C1 and C2, which is a current electrode, and the current lines are shown which are connecting the C1 and C2. Equipotential lines are the lines which are seen in this particular picture, which are produced from potential electrodes P1 and P2. And then you have the voltmeter, you have the ammeter and battery attached to it. This is the setup typically in the field, and then what you have as a subsurface section, which is depicted in this particular picture. And therefore, it is very clear that this is how you can actually measure the electrical resistivity of a given subsurface formation. As I said, this is typically in the text form how the measurements are made, and therefore, you can see that generally the electrical resistivity of the subsurface formation is measured with 4 electrodes, C1 and C2 current electrodes and P1 and P2 potential electrodes. Current of intensity I is introduced between one pair of electrodes, current electrodes, either they are called as current electrodes or also they are named as A and B, or sometimes referred to as plus I, and minus I denoting source and sink respectively. The potential difference produced as a result of current flowing through the medium is measured with the help of another pair of electrodes, which is called as potential electrodes, and therefore, this is typically how the measurements are made. Once this is typically how the measurements are made within the subsurface. Yeah. Once we have the measurements made, there are various ways in which these kinds of measurements can be made, and therefore, we have large number of electrode configurations. We have 3 or 4 different kinds of electrode arrays which are used, which are currently in practice. One of them is dipole dipole. So, we can see that dipole dipole is here in the first picture. Sometimes you have pole dipole. So, you have 3 electrodes, and therefore, one of the electrodes is current electrode and 2 are potential electrodes, and therefore, pole dipole arrangement is there. Sometimes you have pole pole, 1 current and 1 potential, and therefore, you have pole pole arrangement. Apart from these arrangements, the most popular arrangements of electrodes which are used in practice, they are Venner electrode configuration and Schrumberger electrode configuration. In Venner electrode configuration, one can see in the picture that C1 and C2 are the potential electrodes, and P1 and P2 are the potential electrodes, and C1 and C2 are the current electrodes. The difference between the successive electrodes is same in the Venner configuration. On the contrary, the Schrumberger configuration also uses 4 electrodes, and therefore, the difference between the successive electrodes is not same as Venner electrode, and therefore, what you can see is distance between the potential electrode is much less than the distance between the current electrodes, and therefore, it is 1/5 of the distance between the current electrode. The depth of penetration of current in the Venner electrode configuration is equal to A. A is a distance between either C1 P1 or P1 P2 or P2 C2, and therefore, it is the same distance between all 4 electrodes, and therefore, that is defined as a, and depth of penetration is nothing but 1/3 of the distance between the current electrodes in the Venner configuration. Whereas, in the Schrumberger configuration, the depth of penetration of current is 1/2 of the distance between the current electrodes. That is typically how the measurement can be made with the help of these electrode arrays. Once we have the measurements made, this is typically what we can get as a as a typical graph of distance, which is between the 2 current electrodes. So, it is either A B by 2 in Schrumberger, or it could be it could be A in the case of Venner electrode configuration, and major values of the resistivity, and therefore, you will get the resistivity versus distance as a graph plotted with the help of this particular data. This is typically half phase geometry concept. The Venner electrode array is typically what we have is given here, and therefore, in the case of Venner electrode array, one can say that this is the distance which is between the successive electrodes, which is a, and therefore, it can be rho apparent is equal to 2 pi a delta V by I, that is the formula with which you can measure the apparent resistivity. In case of Sumber array, you can see that this is typical formula which is used for measuring the electrical resistivity. Once you have the data collected by any one of these two techniques, then you can make a graph of A b by 2 versus resistivity, that is what we have seen. But when you are in the field and you want to locate the particular spot for the search of the groundwater, then you need to look at which particular spot I should choose for actually finding out the groundwater. And therefore, there are two field methods which are in practice. One of them is known as a resistivity profiling. So, that whole area under consideration can be scanned, and this area is scanned with the help of resistivity profiling. And therefore, in profiling at a constant depth, measurements are made to locate lowest resistivity spot. That is what is done in the profiling. And at the lowest resistivity spot, lowest resistivity spot or resistivity low in a given field, then you can make the measurements by the another technique which is known as a vertical electrical sounding. And therefore, resistivity profiling and sounding are two typical terms that are used in terms of exploration for the groundwater. And therefore, this is what is typically the profiling. Once you have the profiling done, so that you have the grid pattern or any other pattern by which you can measure, or along the profile you can see the horizontal distance and the Venner apparent resistivity graph which is actually made here. And therefore, what you can see is the resistivity response, which is apparent resistivity. And therefore, for different types of lithologies, there is a difference in the apparent resistivity which is actually seen in this particular graph. Normally, in the field, how this profiling is done? You can see in this particular picture that what is normally done is area is divided by grid pattern, and therefore, along this grid at different locations you can make the constant resistivity measurement, and this constant resistivity measurement is actually done with the help of profiling. So, that either by considering this grid, you can then go for iso resistivity contours to find out electrical resistivity low or electrical resistivity high. In case of searching for the groundwater resource, electrical resistivity lows are the target areas from the point of view of finding out vertical variation in the subsurface by using the vertical electrical sounding technique. And therefore, this grid pattern is very important for locating the electrical resistivity low, which is a likely area from the point of view of occurrence of the groundwater. And therefore, this grid pattern is very important by considering the horizontal profiling, to consider for the horizontal profiling. When you have the horizontal profiling done across different grid points, then how to really go for the interpretation is very important aspect. And therefore, the apparent resistivity observations for all the stations along a particular grid or different rows or columns of the grid, this apparent resistivity observations for all the stations which are spread over entire area, they are actually plotted. After this, the contours of equal resistivity values for a particular electrode spacing are drawn and called as equi-resistivity contours. These equi-resistivity contours, as I said, they can give you electrical resistivity low or electrical resistivity high. Electrical resistivity low is the area which is important from the groundwater occurrence point of view. One can also try to have linear maps, as I showed you in the earlier picture here. This the earlier picture in this particular form or in this particular form here, and therefore, it is possible for us to plot the data in various ways, either linear maps or contour maps, and then the lows and highs are actually taken into consideration. This is actually the linear map. We can see only along one transect, one row or column, you can see that the apparent resistivity measured, and the following are the actually stations, and along different stations the variation in the apparent resistivity is measured. Now, let us try and look at the field example of how this particular technique is going to feel, horizontal profiling. For example, in the picture, this is a topographic expression of a dike in a hill that you can see, and in a depression you have this particular picture, which is a well in which there is a dike exposed here. And therefore, in a plain area where there is no expression of a dike, like in a topographic high, then you need to find where exactly dike is located, as dike is a carrier type of dike where the groundwater is likely to occur. And therefore, under such circumstances, horizontal profiling can be undertaken to locate the dike. This is how you can locate the dike, because this is horizontal profiling. These are all different kinds of stations along the x axis, 1 to 12, 1 to 13. These are different types of the stations along which the electrical resistivity measurements were made, and these are apparent resistivity values. Whereas, on the other side you have the apparent resistivity along these stations, and therefore, you can see it is in the form of a linear map or graph that the variation in the apparent resistivity can be seen, and one can see that there is a hump, there is a low along this particular linear graph, and then this particular low coincides with that of the dike feature in the field, and therefore, dike is a conduit type of dike, and therefore, low resistivity is obtained for it, whereas on the either sides this gneissic rock, which is weathered gneissic rock, gives you higher actually values of the apparent resistivity, and therefore, this is possible with the help of profiling to identify the dike features or linear features. It could be lineaments, it could be faults, it could be fractures, or it could be dikes, such kinds of or even certain kinds of utilities, and therefore, it is possible to locate them with the help of horizontal profiling. It is also possible for you, because in certain areas dikes are very important from the point of view of occurrence of groundwater, and therefore, one does not know the different kinds of stages along the length of a dike which will have the occurrence of groundwater, and therefore, along the length of dike, if you really take the measurements in terms of horizontal profiling, then you will be able to get some response something like this. So, that different discontinuous aquifers can be mapped, and this is a discontinuous aquifer along the length of the dike that has been mapped, which is shown in this particular picture, and therefore, there are potential water bearing zones within the dike, whereas there are certain zones which are devoid of the occurrence of groundwater, and therefore, in the field it is possible for us to identify the groundwater by using this particular technique, groundwater resource by using this particular technique. Now, besides horizontal profiling, we also need to see that once you have the resistivity low identified in a given area, you have scanned the whole area by grid pattern, and therefore, you have actually contoured that data, and therefore, you know now where exactly is the resistivity low. Resistivity low is your target area from the point of view of vertical electrical sounding, and therefore, now we have to see the importance of resistivity sounding in terms of locating the groundwater resource. Here, from surface down to the desired depth, we actually find out the resistivity variations vertically and not horizontally. In profiling, horizontally at a constant depth, we are making the types of the we are making the measurements of the electrical resistivity, which is apparent resistivity. Similarly, here from the surface down to the desired depth, maybe 100 meters or 200 meters or 50 meters, whatever it is, we are trying to measure the vertical variations in the electrical resistivity of the rocks, and therefore, this is the depth section, which is actually mapped by vertical electrical sounding, whereas the space section or horizontally spread section is mapped for the constant depth by using the horizontal profiling. That is the basic difference between these two. In the case of sounding, increase in the depth of investigation can be obtained gradually by increasing the distance between the current electrodes. So, as either in the Venner or in the Schrumberger, you can increase the distance between the current electrodes. That means, you are going to higher and higher level of the depth for the investigation, and it is possible with this. And therefore, this gives you information about the depth and thickness of the subsurface layers and their resistivity by using the sounding. In the field, when you are actually applying the vertical electrical sounding, then the procedure for this is a very simple. As I said, you identify the resistivity low, then put your instrument there, and from 1 meter down to the depth of 50 meters, 60 meters, 70 or 100 meters depth, you keep on increasing the distance between the current electrodes, so that you can go to deeper and deeper levels, and that is what is actually done here. In case of vertical electrical sounding, we also get a data with respect to depth versus the resistivity of the layers at different depth levels, and therefore, what we have to look at is the apparent resistivity which is obtained is plotted against the current electrode, because the depth depends on the spacing between the current electrodes, and therefore, current electrode spacing versus apparent resistivity is a plot which is made on log paper to further interpret, and therefore, this is typically what is done in the case of sounding. To get the layer parameters of the subsurface, these sounding curves are actually interpreted, and therefore, the interpretation techniques, they vary. They could be direct methods of interpretation or indirect methods of interpretation that normally we use. Indirect method uses the field curve, depth or electrode spacing between the electrodes versus the apparent resistivity curve, and this curve is actually compared with that of the theoretical curves, which are master curves. There are more than 700 different master curves, which are prepared by many workers like Mahoney, Orella and many others, and therefore, it is possible for us to match the field curve with the theoretical curve and find out the true resistivities. It is very cumbersome process, but these days we have large number of softwares which are automatically going to interpret by iterative technique the different parameters, and therefore, such kinds of softwares are widely in use these days. In the software, what we get is the on log paper horizontal x axis, we have the depth and the electrode spacing otherwise, and you have the apparent resistivity, and therefore, as you go deeper, what kind of graph is obtained, that gives you an indication. For example, in first one here you have the ascending type of curve. Ascending means with depth the electrical resistivity is increasing. That means, theoretically rho 1 is less than rho 2 is less than rho 3, and this is typically what is known as a type of curve. A type of curve is typically devoid of occurrence of groundwater, because as you go deeper, electrical resistivity is increasing, and when the electrical resistivity is increasing, there is no resistivity low which will indicate saturation of a rock formation with respect to occurrence of water, and therefore, no water, that means it is devoid of any porosity, permeability, and therefore, it is devoid of any water in it, and that is typically a type of curve. Conversely, there could be another situation where your curve could be descending type of curve, and therefore, if descending type of curve is obtained, that means rho 1 is greater than rho 2 is greater than rho 3. It means you have the descending type of curve. Here you have the ascending type of curve, which is a type of curve. Now you have the descending type of a curve, which is also known as a Q type of curve, and therefore, this kind of curve is typically indicative of the fact that as you go deeper, there is a likelihood of getting the water, or it could be also low resistivity formation, and therefore, your geological interpretation has to be very sound, and that is how it can be done. In the other graph, you have very typical situation here. In this particular situation, what you have is, with respect to depth, you have the at a shallower level, you have higher resistivity. As you go to deeper level, you have low resistivity, and as you go further deep, you have the higher resistivity. Means your rho 1 is greater than rho 2 is less than rho 3, and therefore, you have typically this is known as H type of curve, and then H type of curve indicates that there is a resistivity low at a shallower depth, and therefore, this is typical scenario in case if geologic or hydrogeological conditions favor, then it means that you have the possibility of getting the groundwater at a shallow depth, ideal situation for tapping the water by taking a dug well, and that is how it is there. In contrast to this, you could get a situation where your top layer, first layer near the surface, could have the resistivity which is less than the middle layer, and middle layer will have higher resistivity than the lower layer, and therefore, it is a bell type curve, which is just opposite to what I said as a H type of curve, and therefore, this bell type curve indicates that rho 1 is less than rho 2 is less than rho 3, and therefore, you will have low resistivity for the third layer, deeper layer, but high resistivity for the middle layer. It means that at a deeper level, you could get resistivity low, which will indicate the occurrence of possibility of groundwater, and that is something which you can interpret with the help of these types of the curve, which is typically done by matching the field curve with that of the theoretical curve. It is possible with the help of software also to find out two-dimensional geometry of the aquifers within the subsurface, and therefore, geometry of the aquifers is reflected in this particular picture here, which indicates linear stretch of aquifer at a shallow depth of up to say 20 meters. On your left side, there is a y axis which indicates the depth, and then the right side, which is the scale there, which indicates the values of the resistivity. Blue color indicates low resistivity. Low resistivity would coincide with occurrence of groundwater, and therefore, this particular picture indicates that up to say 20-30 meters, you have linear stretch of aquifer actually spreading across a larger distance, and therefore, you know the thickness of this particular aquifer, you know the extent of this particular aquifer, and therefore, based on this you can recommend the location of a well in a given area. This is typically what you get as a two-dimensional aquifer geometry. Sometimes it is possible for you also to find out three-dimensional aquifer geometry, how the subsurface layers are saturated with respect to the occurrence of groundwater, that also can be found out with the help of this particular three-dimensional geometry of the aquifer. And therefore, in this picture we have the linear slices at a different depth taken at 5 meters depth, 10 meters depth, 30 meters depth, 45 meters depth, 60 meters depth, and therefore, you know with the help of these slices, if you take the slice of the subsurface at a 10 meters depth, then you know that major area is a linear stage between two resistivity highs, which indicates the presence of groundwater. Then this particular area between two resistivity highs also continues up to say 15 meters or 20 meters depth. That means, there is a groundwater occurrence up to the shallower depth, but as you go deeper up to 30 meters, then the continuous occurrence of groundwater cannot be seen, because the area occupied by the resistivity highs on either sides is increasing, and the resistivity low occupied area is actually getting isolated. So, there are 3 resistivity lows in this particular picture, indicating these are local spots of occurrence of groundwater at 30 meter. And as you go deeper to nearly 50 meters, then you see that many resistivity lows are obscuring, and whole area is almost occupied by resistivity high, with only small patch of resistivity low in between, and therefore, that is only isolated occurrence of groundwater. And then if you go to 70 meters depth, then that situation also prevails. It means that your location has to coincide with only that particular resistivity low, then and then only you will be able to tap the groundwater. It is very typical scenario that you can gauge with the help of this particular technique, and therefore, electrical resistivity technique can give you a fair insight about the occurrence of the groundwater and the 2-dimensional and 3-dimensional aquifer geometry of a given area. This is typically how this particular technique can be used in search for the groundwater. Thank you very much.